All right. Good evening, everyone. So this is our last week that we will meet and discuss. So I hope today is also there is no audience, but anyway, it's fine. So what I will do today is I will go through a problem on component matching, especially for single spool turbojet engine. You can extend that same methodology or the principle for two spool and two spool turbojet, or for turbofan engines you can extend those arguments even for turboshaft engines. Um, so that is what we will do today, and if you have any doubts, what you can do is probably you can ask in the common forum, and I will be able to look at it, and you can I will be able to resolve your doubts if you have any until your exam. I hope around 26 or 28 is October is your exam, I guess. Uh, all the best for your exams. So with that short note, what we will do, we will uh, quickly get into today's topic. Mm, in this week 12, it's actually an important week. It's an advanced concept compared to whatever we studied till now. Advanced in the sense, just um, till now we studied on how to design an engine, or how to evaluate certain parameters of an engine, and upon varying certain parameters what happens in an engine, separately each component when it behaves with its efficiencies, uh, with its characteristics, each component separately, when you assemble together, this is how it behaves. That is what we studied till now for any gas turbine cycle. um, this time what we did is, once we have the finalized engine, if I have the same engine at a different operating conditions, how my performance is going to vary. So that is where this component matching principle is coming in. That is what we saw in the lectures also. And final one or two lectures was on engine performance testing, and those are typical uh, theory kind of questions. So I hope there are a lot of questions you are yet to answer in week 12 assignments. Although there are no problems to solve for week 12, but I I hope even me and Professor Chetan Mistry thought it would be very helpful if we could solve a single spool turbojet engine component matching problem. That is what will be giving you confidence on how to evaluate performance for off design condition, because this problem we really didn't uh, solve during the lectures. So that's why we decided for week 12 we will solve a component matching problem, and that would be very helpful for you guys to understand. um, y- we have Krishna Kumar here. Thank you, Krishna Kumar, for joining. All right. So what we will do, for single spool turbojet engine, we all know what is the turbojet engine, and so we all know the turbojet engine, especially single spool turbojet engine. We solved it in week 3, right? And on top of it, we built a lot of things on top of this turbojet engine. This is the first engine that we studied, and on top of it, we built a lot of things, and we came up with the different variants of gas turbine engines from this turbojet. So this is the most simplest basic aero engine cycle that you will come across. Mm, now, if you so we all know what are the components, and how we do it, everything we know. So we will directly jump into a problem. So uh, let's say you have a single spool turbojet engine. It's a small turbojet engine, okay, and you have designed the turbojet engine for ambient condition. Okay, when I say design, you have selected pressure ratio for the compressor, you have selected the turbine, you have selected the combustion chamber, and also um, the fuel flow rate for a required thrust. So all these things we have, uh, we must have done, and also at the end of the day we also will get area of the nozzle, A9 basically. So once you got A9, that actually fixes entire engine, and this is the engine you have, which is designed for certain ambient, certain pressures and temperatures. Usually that design point will be in ambient condition. Okay. And also for ground condition, usually the engines are designed because during takeoff you will have very high thrust. You need very high thrust, so that will be uh, so that will be uh, obtained only at the ground condition. So that's why people design it for the ground condition, so that you can have a very high takeoff thrust. And then your off design point would be something like a cruise condition. Okay. So in cruise condition, ideally the engine was not designed for the cruise condition. So that's why when it is in cruise condition, we say it as an off design point or off design uh, condition for this turbojet engine. So that's the just the terminology. Okay. So here we have single spool turbojet engine, and which is designed for ambient pressure and temperatures of 101.3 kilopascal and 288 Kelvin. And the compressor pressure ratio is 5, turbine inlet temperature is 1200 Kelvin. Total pressure loss in the combustion chamber is 6%. Fuel heating value is given, and core engine mass flow rate is 19.64 kg per second. This is at ground condition. Okay. So so each component will have its own efficiencies and losses. So those also we have added. Now, additionally, there are few things which are given in order to solve something, in order to solve this engine for an off design condition. Okay. The first one, that information that we need is the compressor characteristics or the compressor map. Okay. In a compressor map, what you will have is you will have a corrected mass flow rate, and you will also have a pressure ratio, and efficiencies, and the ISO, what do you call it, ISO speed lines, or uh, the the pressure ratio of the compressor is going to depend on mass flow rate and the speed at which it is rotating. So this compressor map will establish a relation between this mass flow rates and speed, and also the efficiency of this compressor. Okay. Um, Now, for this problem, for simplicity, what we did is we decided not to include the speed of the compressor also. So here we are just having the mass flow rate uh, effect on the pressure ratio. Okay. So you can ideally plot this. You can ideally, here I have represented it as a table, but you can also plot it and you can see for yourself. And we have also seen this kind of compressor map and turbine map for in our lectures also. So I strongly advise you to take a look at the lectures. Okay. So in the compressor characteristic map, what we have is I have three pressure ratios. 5 is the design point, 4.5 and 4 pressure ratios also there, and corresponding mass flow rates and efficiencies are given. Similarly, we also have turbine characteristics. Again, for simplicity, this problem, we are going to assume that m dot c4 is nothing but mass flow rate, corrected mass flow rate at the entry of the turbine. Okay. And usually it is chalked, so that's why we are going to, it is not going to vary based on the pressure ratios. So uh, we will consider it to be a constant, which is 8.9463 kilograms per second. And also since m dot c is also constant, eta is also, we are taking it to be constant, to be 0.87. Okay. So these are additional informations that we need. um, so um, if we so we can actually solve this numerical for the design point for ambient condition, and we can get thrust TSFC, and we can find A9, basically the uh, area, exit area of the nozzle. uh, but that is going to take a lot of time. So what I did, I already solved it for design point. We are now interested in component matching problem, right? So I've already solved for design point, and these are the results we have. So this is for design point, our exit area is around 0.07346 meter square, and the velocity of the gases at the exit will be 579.79 meters per second. Now the thrust it produced was 12.934 kilonewton. So this is at ground condition. So whatever the off design point you are going to have, it's going to produce lower thrust than this. Okay. Um, I mean, usually it should be lower thrust unless you have some very high speed. Let's say you're operating at a very supersonic speeds. Then you might able to see, but in reality you will not be able to see because you need to uh, maybe the compressor and turbine may not be uh, able to handle such supersonic speeds. So, okay, anyway, so those are not relevant here, but this thrust is what you got for the ground condition, and TSFC and thermal efficiencies are given. Now what we are asked to do is, so this is the design point. You can also do the design calculation and then you can come up with A9, V9 and T, and this is going to be something like this. Now what has been asked in this problem is, now if I want to so this is designed for ground. Now I want to fly at certain altitude. Okay, so here let's say you are cruising at altitude of um, 7,000 meters. Okay, when you are cruising at that altitude, what is going to be your P infinity? So what is going to be your turbine entry temperature, mass flow rate, thrust, and fuel air ratio is what you have to find. Okay, so the mass flow rate also changes because your altitude has changed, and at 7,000 meters altitude we have P infinity and T infinity, which is also already given. Now this is an off design condition because we haven't designed for this particular uh, case. So that's why we call it off design condition, and we need to find out what is the turbine entry temperature and what is the corresponding thrust that we are getting, that we are producing. Okay, so the T04 is like a lever that we use to uh, change our fuel flow rate, and because of that your thrust is going to vary. So that's why if we know T04, it is something like we know uh, what should be my lever settings. Okay, something like that. You can think like that. So anyway, from the component matching problem, we are interested in finding T04 thrust, mass flow rate, and fuel air ratio. Also, compressor pressure ratio. Um, in this, in this problem, um, how are we going to go about it, right? So we will actually start with, you know, recapping all the equations that would be relevant for our problem, for the present problem. Okay, for detailed understanding I strongly recommend you to go and visit uh, the first three lectures of uh, week 12. Okay, all right. So we what we did basically is we took every component, and we connected with the subsequent component, and what we did, we applied certain laws. That is a universal laws, right? Like law of mass conservation and also energy conservation. So we apply these two laws at junction of every component in order to analyze its performance when it is at the off design condition. Okay, so now the performance of each and every component will not be decoupled. It will be coupled with other components. Okay, so we will see more about it now. First component that we have is inlet and compressor, and you are trying to match this inlet and compressor. And the only thing happening between these two uh, components is the mass flow from inlet to compressor, and we know based on mass conservation, whatever mass that enters the inlet is going to, it should enter the compressor. Okay, because this is a simple turbojet engine. So this is the condition that we have, and uh, for the inlet we know P02 and T02 we can find based on M infinity, and if M infinity is given, it is going to be straightforward for you guys to find out. Now uh, the next component that we have is the compressor and combustion chamber matching. Now here what you have to notice, again the mass conservation is the main thing. M dot which exits the compressor, or M dot which comes inside the compressor, should be, here we denote it as M dot 2, which should be equal to 1 plus F m dot 4, because at the end of the combustion chamber you are going to in the combustion chamber you are going to add fuel. So your mass flow rate, I guess it should be opposite. M dot 4 should be equal to 1 plus F m dot 2. Okay, so this I will update. Now you also need to, so if you want to know pressure at the exit of the combustor, you can actually find out based on uh, P04 by uh, P04 by P03 is nothing but the pressure loss in the combustion chamber, times P03 by P02 is nothing but the pressure ratio of the compressor times P02. P02 is inlet. So we already know what is going to be our P02 if we know the M infinity, the flight condition. Okay. And one more thing I think I forgot to mention here is the off design condition is for flying condition of Mach 0.8. Okay. All right. Um, and the other conservation equation that we have is energy conservation. So we all know we are adding some fuel. So this is nothing but the fuel to air ratio equation. It's just written in, it's just divided by T02 in both numerator and denominator. That's why it is strange looking here at this place. But the what do you call, the equation is just the energy conservation at the combustion chamber. Okay, and the third one we have is compressor and turbine matching. Okay, now the turbine has to drive the compressor, so it has to mechanically the energy has to be transferred mechanically, and so whatever the energy generated by turbine should be equal to the energy required by the compressor. So this effect, so if turbine generates lower energy, that is going to affect the compressor pressure ratio, and if the compressor pressure ratio is low, then it is going to affect the inlet. So you can see the connection. So it is going to have a so having changing something in the turbine is going to affect the flow at the inlet. Okay. uh, Here again we have mass conservation. Here I have written in terms of corrected mass flow rate, and for more information, again, I would request you to go through the lectures. It is just same thing. The mass conservation here is m dot 2 is equal to m dot 4 into sorry, m dot 2 m dot 4 is equal to 1 plus f m dot 2, the same mass conservation that we saw in the previous section. Here I just rewrote in terms of corrected mass flow rate. That's it. Okay, it's algebraic manipulation of the same equation. And we also have pressure ratio across the turbine we can find using this formula, and the temperature ratio across the turbine we can find using the energy conservation. So here is where we use energy conservation, and you can notice that the temperature ratio of the turbine also depends on temperature ratio across the compressor. So this ensures that component of the turbine and compressor is matched properly. And then we also have additional equation here, which is m dot c4 by m dot c5, which is corrected mass flow rate, ratio of corrected mass flow rate from inlet to outlet across the turbine, is equal to pressure ratio across the turbine by temperature ratio across the turbine. This is also simple. uh, Basically it is coming from mass conservation within the turbine. M dot 4 is equal to m dot 5 if you take that as your equation, and then if you rewrite in terms of corrected mass flow rate, you will end up having this, you know uh, equation. So it's just a simple manipulation of same mass conservation. And the next component that we have is turbine and nozzle we need to match. Okay, for this, whatever the mass flow rate comes out of turbine, uh, it uh, it has to go through the nozzle. Now if the nozzle is chopped for the same pressure ratio, if you end up having a more mass flow, it cannot allow the mass flow to it cannot allow higher mass flow because the nozzle is already choked. Okay, so please understand, there is a nozzle which is designed for some A9. Okay, so once you fix the A9, and if you say nozzle is choked, so for ground condition nozzle is choked, now the mass flow rate through the nozzle will not vary unless there is a change in the inlet pressure. Okay, uh, or in other words, if you change the pressure ratio across the nozzle, let's say P05 by P9, uh, the mass flow rate will not vary at all. Okay, mass flow rate remains constant. Now, if the if you increase the fuel flow rate at the combustion chamber, that will increase the mass flow rate at the exit of the turbine. But the nozzle cannot, while you have pressure ratios to be same, the nozzle cannot handle that higher mass flow rate. So what this does is this tries to have a uh, so have a other it tries to affect all the other components that is at the front. How does it affect? Because when the mass flow rate increases, in order to in order to allow this mass flow rate through the nozzle, the pressure at the exit of the turbine will start rising. And if the pressure at the exit of the turbine, which means it will try to change the pressure ratio in order to allow this higher mass flow rate, which means it will increase the pressure ratio to a higher value. Now, if the nozzle exit pressure becomes higher for the same sorry, if the turbine exit pressure becomes higher for the same turbine entry pressure, then the amount of work it has extracted from the turbine will be less. And if the amount of work extracted at the turbine is less, the amount given to the compressor is less. And if the amount of work given to the compressor is less, the pressure ratio across the compressor will be less, which again affects the combustion chamber, and again it will be a negative feedback loop from the turbine. It also does uh, the it also affects the inlet flow rate. So because the compressor pressure ratio is less, the the amount of mass the compressor can swallow will also reduce, right? So the A infinity, in other words, A infinity is the projected area from which mass is entering the engine, that will reduce. Okay, if that reduces, the mass flow rate again reduces. If the mass flow rate reduces, everything again comes back to equilibrium. So that is how the entire engine adjusts itself to an equilibrium state. It cannot happen, it cannot work in a non-equilibrium. But as a separate component, everything can work at all the mass flow rates. But all these components are connected together. You have certain constraints of the nozzle will affect ultimately the inflow of your engine. Okay, and also in between, and also all the components in between. Okay, so that is the idea that we are trying to capture using this problem. Okay, so this mass conservation is again same thing, is just it just looks like this because I wrote it in a peculiar way, but it is the same mass conservation equation, which in terms of mass flow rate parameter that we usually used to write. Okay, so RC, you can notice here it's a m dot 9 here, which is nothing but rho 9 a9 v9, and the rho 9 a9 v9, if you try to write it, you'll end up having this kind of thing. Okay, based on choking condition, you will change these two parameters and will have a different expression. And based on that, you will find whether the mass flow rate at the nozzle is equal to the mass flow rate entering the nozzle. Okay. Mm. Now, the choking condition we all know. And for the chalked nozzle, this is how the relation looks. And for unchocked nozzle also, this is how relation looks. Just I wrote it in a different manner. Okay. Um, Okay, let's see. But so we have discussed a lot of formulas till now, but we also need to know how we are going to solve this problem, right? So what is the methodology to solve this problem? So I have already designed my this thing engine. Now I just want to test it at a flying condition. Okay. Now if you want to do that, uh, you have to these many equations, you have to solve it together. So instead what we do is we try to make a more involved approach, where we initially try to guess the pressure ratio. Okay, so let's see, for the known flying condition and efficiency of diffuser, you can actually find T02 and P02. Okay, so if the flying condition is given, let's say m infinity is given, and we also know the ambient condition, so we can easily find T02 and P02. This is not a big deal. Like, this is what we usually start our turbojet calculations. Okay, now The pressure ratio we don't know for the flying condition, because it is not we it is an variable parameter, and we have to obtain the you have to solve the problem, and you have to obtain pressure ratio from it. So in design problem, we the pressure ratios are all given. Okay, and we design, let's say, the exit area of the nozzle. Here we are given the engine, and you are expected to find out what will be my pressure ratio of across the compressor. I mean, if I want to fly at this condition, what is the pressure ratio happening within the compressor and also turbine. Okay, so this to do that, what we do is, we first, let's say, we will choose a P03 by P02, which is nothing but pressure ratio across the compressor, and we do entire calculation, and we will see whether this mass flow rate, both mass conservation of mass and energy, whether it is matching at every location. Okay, and only if it is matches, then we will go forward with that pressure ratio. If not, we will change the pressure ratio and repeat the exercise again. So that is our second step. So second is to find the pressure ratio, and based on pressure ratio, we have a compressor map we have already discussed. From the compressor map, you will get corrected mass flow rate, m dot c2, and efficiency. Okay, in our case it is given as a table. Now, the next thing, once you choose the pressure ratio, what you have is, you can actually find the temperature ratio, because you know the efficiency of the compressor, you know the pressure ratio, then you can find the temperature ratio. So once you know the temperature ratio, you don't know the turbine entry temperature also, because that is not a this is you're not working on design condition, right? So you don't know turbine entry temperature, you should also find that. For that, you need to know fuel air ratio, which also again you don't know. So what you do is, you assume f to be 0, and then try to find out uh, the T04 by T02. So for that, you need additional information called m dot c4 and eta t. Okay, so it is again from the mass conservation. So whatever m dot c2 comes, it has to go through the upon adding fuel, it has to go through the turbine. Now, the turbine characteristics, turbine map that we have, the table that we have for turbine, it already gives us m dot c4 and eta t, right? So you can use these informations to arrive at both f and T04 by T02. Now that we have assumed some f, using this you can actually find out T04 and T02. And using T04 by T02, um, here, I mean, it is equivalent to say we have also found T04, because we already know T02. Okay, using this T04 by T02, you can actually find out what is your fuel air ratio. You can go one step back and see, in the combustion chamber, my temperature rises from T03 to T04. Now, since I know T04, I can actually find out what would be my fuel air ratio. Now, if you find a fuel air ratio, and if that fuel air ratio is same as what you have assumed, then you are good to go. So f and T04 by T02 are consistent with each other. Now, if it is not, you have to modify f, and you have to again go back to turbine map, find the m dot c4 and eta t, and you use the mass flow rate matching. Okay, and then find the T04 again. So you have to do this until you find the proper f. So once you know f and T04 by T02, you go forward with the turbine. In the turbine, uh, we you can find out tau t. Okay, and based on how, so we do this energy conservation from turbine to compressor, right? And based on that energy conservation, you can find the tau t. And once you find tau t, you can find pi t, and once you find pi t, you can actually find the gas generator pumping characteristics. So what is this gas generator? Is nothing but this compressor, combustor, and turbine. These three components together is what you call gas generator. If you attach a inlet and then nozzle to it, it becomes a turbojet. If you attach a inlet and shaft, free turbine to it, it becomes a turbo uh, shaft engine or turbo prop engines. Okay, so that's the difference. So a gas generator is a common terminology. So across the so this gas generator, you can see view it as a whole component, and you can say gas generator pumping characteristics like P05 by P02, T05 by T02, and m dot c5 you can find out. So once you find this m dot c5, see, till now this m dot c5 is the mass flow rate, and till now it doesn't know about anything about the nozzle. Okay, but the nozzle is already designed for some area, and if let's say if you say it is chalked, then there is no way you can have a different mass flow rate at the turbine exit while the mass flow rate is already chalked at the nozzle. Okay, so that matching you should do. How would you do? So you use the pumping characteristics, and based on appropriate chalking condition you find uh, pressure ratios, and then you find m dot c9. Okay, so now this is the mass flow rate going out of the nozzle. Now you check whether this mass flow rate which goes out of the nozzle is same as mass flow rate that we got at the turbine exit, and if these two are same, then you are good to go. All the components are matched, and you can use whatever T04 by T02 is the fuel flow parameter that we are uh, leverage parameter. What do you call? Um, uh, yeah, the parameter which you try to modify in order to get different thrust, right? If not, what you have to do, you have to modify the pressure ratio. Okay, again, so whatever the pressure ratio that is at the start, we chose some pressure ratio for the compressor. We have to modify that pressure ratio until we match this mass flow rate uh, m dot c9 and m dot c5 correctly. Okay, until then we cannot go forward with the calculation. So let's say you have matched, then your matching is complete and you can go forward and find the thrust and whatever they have asked for. Okay, so this is what we are going to do for this present problem. um, so as I said, it's going to be for cruise condition of Mach zero point 0.8. So if you do, you can actually find P02 and T02. It is going to be around 61.6 kilopascal and 273.77 Kelvin. Okay, and now let's say we begin with by choosing pressure ratio of 5. Now with this, you can take a look at the table that I showed before. It is going to provide you m dot c2 and eta c to be 20.165 kilogram per second and 84% efficiency. Okay, so this is coming from that table. So this is where you need to use that table, or if map is given, you need to use that map to get the m dot c2 and eta c. So once we have m dot c2, we have also found pressure ratio. We can actually find temperature ratio across the compressor, right? And then you can use this m dot c2 and tell that in addition to m dot c2, at the end of the combustion chamber I would add some fuel, and because of that fuel it would my mass flow rate increases to m dot c4, and then you match these two to get f and t04. Okay, so that is the next step, as I said. um, so in addition, P4 you can find, this is known. Tau C, as I said, you can find the temperature ratio across this compressor, and then for you can get the normal operating line. The operating line is nothing but the T04 by T02 that we are interested in. So for that you need to do mass flow rate matching. Okay, so mass flow rate m dot 4 is equal to 1 plus f times m dot c2. Okay, now this will be uh, so m dot 4 is equal to 1 plus f times m dot 2, and if you just rewrite m dot 4 and m dot 2 in terms of m dot c4 and m dot c2, you will end up having this relation. This relation we also saw in the lectures. Okay, so please take a look at it. Now the thing is, we don't know both f and t04 by t02. That is the problem. So what we do, we assume some f. Okay, we can start from 0 and we can do this calculation again and again. So I have already done that. So uh, that's why I'm going to take a very better initial guess. That initial guess is going to be 0.0204. Okay, so that is my initial guess. This is how AF would be. And if so, once you know this F, m dot c4 already we know from turbine characteristics. M dot c2 we have already known from the compressor characteristic. P04 by P02 we already know because pressure ratio across the compressor we have chose, and burner pressure loss we already know. It is a given parameter. So based on that you can find T04 by T02. So that is the whole point. So you can find you can rearrange this equation, you can substitute these numbers, and you will end up having T04 by T02 to be 4.1765. Okay. So this is the normal operating line that we are going to operate it. Okay. And the next, as I said, once we know T04 by T05, you should T04 by T02, we should know whether that temperature can be achieved with the fuel air ratio that you assumed before. Okay, so for that you do energy balance. We already know this fuel air ratio problem. I mean fuel air ratio expression, which comes from the energy balance at the combustion chamber. If you substitute this number, you will indeed get F to be 0.0204, which is same as our initial guess, because I already did this calculation. I know this. If you take this as your initial guess, you're going to get this. Okay. If you don't know, you just start with 0 and then do this calculation repeatedly twice or thrice. By the end of third iteration, it will converge to this value. So mostly second or third iteration, it will converge to this value. So now we have found out two things. One is F and T04 by T02, where F is 0.0204 and T04 by T02 is 4.1765. All right. Now what we need to do is, now we need to match the turbine work to the compressor work, and that was going to give me what is that is going to give me the uh, temperature ratio and pressure ratio across the turbine. Okay, so that is what we are trying to find out now, the temperature ratio across the turbine. If you here in this equation, we know everything. Mechanical efficiency is 98% in this problem, so you can substitute those numbers. F and T04 by T02 we just found out, and tau c, we know pi c, we can find the tau c. We also did that in the last slide. So if you substitute this, you will end up having tau t to be 0.8551, and with the tau t you can also find pi t. Pi t is nothing but pressure ratio across the turbine, which is P05 by P04, which is 0.4798. Okay, so this tau t is important, so that this one we are going to use it for the upcoming calculations. Okay, now let's summarize. Still now, what is the pumping characteristics? Still gas generator. So you can remember that we had this m dot c5 term, which is exit at the exit of the turbine. What is my corrected mass flow rate? So you can calculate this, and it will come out around to be 17.24 kgs per second. So this is not the mass flow rate, exact mass flow rate. It's a corrected mass flow rate. So please remember that. And what you have is, you can P05 by P02 is also one of the characteristics, pumping characteristics for the gas generator part of the whole engine. And that again you can find out by multiple subsequent pressure ratios from across the turbine chamber and the compressor. You can find out to be 2.2550. Okay, so from the inlet of the compressor to the exit of the turbine, you have a pressure ratio of around 2.25. That's the concept. Okay, so in the compressor you have a 5 pressure ratio, and in the turbine you have a reduction in pressure ratio. So overall there is a increase in pressure across this compressor combustion chamber and the turbine, which is around 2.250. So that is something you can note. And if you can actually find out the P05 also, which is 138.91 kilopascal. And then similarly you can find T05 by T02, which comes out to be around 3.5712, which is expected because we have added fuel in the combustion chamber and we have combusted, so some heat has released in the combustion chamber. So at the exit of the turbine we are expected to have a higher temperature. All right, so T05 would be something like 977.67 Kelvin. So these are the characteristics that we found. So this is until turbine, and we have also find m dot c5 17.24 kg per second. Now this is the P05 is given. Based on P05 and ambient condition, we already told that for ground condition it has chalked. So as you go higher in the altitude, there is no way it is going to be, you're going to become unchalked. Okay, so that is not a option. It is going to be always chalked. So if it is chalked, for this P05, for this inlet total pressure, if the nozzle is chalked, its mass flow rate is fixed. Okay, but that mass flow rate information we haven't used anywhere till now. Okay, so that is something you should note. Till now we never used that mass flow rate through the nozzle in our calculation. but we already found the mass flow rate, that is to be 17.24 kg per second. Now, only if the mass flow rate through the nozzle is same as this 17.24 kg per second, then this engine will operate in that condition. If not, you need to do this iteration, change the pressure ratio until you match these two mass flow rates. Okay. Um, let's solve this. I think you will better understand once you see how it is done. So this is where it comes, turbine and nozzle matching. First thing you have to do is you have to do the critical pressure. You have to find the critical pressure. For critical pressure, we already have a relation. uh, first you need to know whether it is chalked or not, so you can do this calculation. And P05 by PC, it's actually a function of gamma and eta, so that is not going to change because of change in pressure, so that is going to be 1.9168. Now uh, now we already know P05 from the pumping characteristics we have found out. So based on that, you can find the critical pressure to be 72.47 kilopascal. And as we expected, the outlet pressure, the exit ambient pressure is 41.06 kilopascal, which is lesser than the critical pressure, which means nozzle is chocked. So nozzle is indeed chocked. It was chocked in the ground condition. Now even at the flying condition, the cruise condition of 7,000 meters, it is still chocked. Let's go ahead. Now, these two, there are two, expressions that we wrote in terms of V9 by root of T9, just to, quickly find out what will be m dot C9. So that's the whole point of expressing it like this. So since it is chalked, it's going to be V9 by square root of T9 is 19.5374. And for and the other parameter that we had was P05 by square root of T9. So that also you can find out to be 4795.1052. So these are not just numbers, it has its some units, okay, because you can see that it's V9 by square root of T9. So it's going to be meters per second by uh, root of Kelvin. Okay, so but this is something it has we are not interested in. So I mean, you can add the units here, but we will directly substitute it in the mass flow rate expression. Now the next thing that we have is mass conservation. As I said, for the nozzle, if you say P05 is this much, here it is like 138.1 kilopascal, then the mass flow rate of the nozzle is already dictated by that P05. It has nothing to do with the inlet mass flow rate. Okay, um, so that we will calculate. So m dot C5, or this is also equal to m dot C9. Okay, because it's a nozzle, right? So from m dot C5 calculated based on nozzle characteristics, are calculated based on P05 pressure at the exit of the uh, turbine. Okay, that would be coming something like 17.259 kilograms per second. And you should note that it was before previously from mass flow rate. Okay, from matching the gas generator with the inlet, the mass flow rate came out to be 17.24 kg per second. Now you can see in the nozzle it is coming out to be 17.259 kilograms per second. So these two are not really equal, but for the sake of simplicity, you can say these are equal. You can actually arrive at equal mass flow rates uh, in both the sides by tuning the pressure ratios. So we have taken it to be 5, and if you tune it, it will be like 4.98, something like that, 4.9. So I don't want to do that, I will leave it up to you guys, but this is a very well matched mass flow rate, you can say for sure. So a 17.25 and 17.24 is not a big differences, so you can say the pressure ratio across the compressor is still 5. Okay, now that so this will make sure the matching is complete. So that actually the whole reason to choose a pressure ratio of 5 initially is because I already did this calculation, and hence I know at 5 it is going to match properly, so that's why I chose that. You can actually start from 4, and if you would have started from 4, you have to do this calculation again and again until you reach pressure ratio of 5. Then only you will know that matching would be complete. Okay. So since I already know the value, I just took it as an initial guess so that I don't need to do that iterations. But you should understand the logic behind it. If you find m dot c5 from both from the turbine and from the nozzle, if you find it is not matching, then you have to change your pressure ratio and you have to repeat the calculations again. Okay. Now, yeah, so that is what is being written here. The corrected mass flow rate dictated by the nozzle is 17.25. When we say dictated by the nozzle, it's dictated by the pressure entry, right? Pressure, uh, uh, total pressure at the entry of the nozzle. Okay, and but the corrected mass flow rate from the turbine exit is 17.24. So that is dictated by the mass conservation coming from the compressor to turbine. Okay. Here we are assuming to be they are almost equal, so we'll take the choice of pressure ratio that we selected at the start of problem is correct. Okay. If it is not matched, you need to change the compressor pressure ratio and you should repeat this calculation until you see m dot c5 to be matched when you use both the formulas or both the expressions. Okay. Now let's find the operating conditions to get this off design point. So that is first thing is T04. So the T04 is coming out to be around 1143 Kelvin. So this is nothing but we already found T04 by T02, which is 4.71 something. That I multiplied with 273.77, which is T02. Okay. So this is how you get T04 1143.4 Kelvin, and then you have fuel air ratio, which is 0.0204. In fuel air ratio for the design condition was 0.02143, so it was fuel air ratio is a little higher. Here it is a little bit lower. And m dot infinity, you can m dot infinity is nothing but the mass flow rate at the entry of the nozzle. Okay. uh, Sorry, entry of the inlet, m dot infinity, so that will be equal to m dot 2, right? We already know m dot c2, so based on m dot c2 corrected mass flow rate at the compressor, because when you fix the pressure ratio your m dot c2 is fixed. Based on m dot c2 you are trying to find out the m dot infinity. Okay. Now for this m dot c2, if you rearrange this, you can find the m dot 2, and m dot 2 is nothing but equal to m dot infinity. So if you substitute corresponding numbers, you will end up having m dot infinity to be 12.248 kg per second. Okay, this is the mass flow rate entry to the compressor. And the next thing is performance parameters we are interested in. So for that we need to find the velocity and the pressure at the exit of the nozzle. For velocity at the exit of the nozzle, you can express, we all know it's going to be sonic because it's chalked, and you know all these relations. So at the end of the day, we will get velocity to be 565.98 meters per second. And the pressure at the exit of the nozzle will be equal to critical pressure, which will be 72.47 kilopascal. Okay. Now, um, what we have is we have found velocity and pressure. Now we will find the thrust. Okay. The thrust, this is we know how to calculate the thrust of a turbojet engine. V infinity is based on the m infinity, which is 0.8 for this off design point. Now if you substitute these numbers, V infinity corresponding to mark of 0.8 is nothing but 249.82 meters per second. V9 we just found out, and F and M dot also we found out. P9 is 72.47 and the P ambient is 41.06. And A9 you should note here, A9 it is coming from the design condition. So once you here the turbojet engine has a fixed area nozzle. Okay. Now if you have a variable area nozzle, then you have more control actually. So now you no need to actually do the matching of turbine exit mass flow rate and the nozzle uh, mass flow rate, because whatever the turbine exit mass flow rate, whenever the mass flow rate coming out of the turbine, you can actually expand your nozzle, right? Change the area to adjust your nozzle in order to take all the mass flow rate out, so such that it will not affect the compressor and ultimately at the inlet. Okay. So if it is a variable area nozzle, then you can uh, change your area in order to decouple the effects of nozzle on the other components. Okay. All right. So the thrust here is coming out to be 6.3213 kilonewton. We will compare that with the design point soon. And the TSFC again you can calculate based on this, and it comes out to be 0.1423 kilograms per hour per newton. Okay. Efficiency, I have calculated only thermal efficiency. You can actually calculate propulsive and overall efficiency too. The thermal efficiency for this engine comes out to be around 31%. Okay. So this is the final uh, comparison that we have here. The A9 is same, so that is please note that. Okay. So A9 is same. V9 is here. V9 in the design point was 579.79 meters per second. Here you have a higher V9. Okay. And the thrust at the design point was around 13 kilonewtons, but here you have only half of it, 6.3 kilonewtons. Okay. And the TSFC is higher because it is not designed for that condition, so it is expected to be higher. And thermal efficiency comes out to be 31%, but if you have to calculate the overall efficiency, I think it will be very bad in terms of propulsive efficiency, because um, flight is engine is flying at 290 meters per second, but the exit velocity is like 600 meters per second. So you need to find the thermal efficiency and multiply to get the overall efficiency, and then you should compare that values. Okay. Anyway, because why I said that is TSFC, you can see it is higher, so I would probably expect the overall efficiency to be uh, lower than the thermal efficiency that we see at the design point. Anyway, that is secondary, doesn't matter here. So here on the design point, m dot was 19.64 kg per second, and the off design point m dot was around 12.248 kg per second, and the T04 is 1200 Kelvin, and for this condition you should have only T04 around 1143 Kelvin, a little slightly lesser. Okay. So there are few things that you should understand here. This is just a basic a problem that we solved. Actually, we didn't do uh, a little, so we didn't take into account of speeds. For example, we didn't match the speeds of turbine and compressor. In fact, we didn't even take that into account. So in addition to what we did till now, you also take NC4 also into consideration. Okay. The NC4 and NC2 also should be taken into consideration. Okay. But in order to show you, I took a simple toy problem uh, to show you how this can be done, and how this can be extended to other engines. Also, uh, what we did was mass conservation, energy conservation, mechanical coupling, that we matched for all these components. But what we didn't do is geometric matching. We didn't do. Okay. For example, we didn't find A infinity. We didn't find MZ2, A4, and A8. All these things we didn't find, right? So ideally you should also include those equations, then you should you know redo these calculations, and that will be more realistic, what do you call, uh, you know of design parameters that you will get. Okay. So here we can see even at the design point and both in design point and off design point, our pressure ratio was almost same. So both was 5 only for now, but ideally your pressure ratios will be different. Okay. Because when you have the when you couple the n also, and you also take into account of m dot, which will be varying because of A infinity. M dot infinity will vary because of A infinity. for here what we found, we just took m dot infinity to be same as from the m dot c2 from compressor map that we took, right? But the compressor maps m dot c2 should also come from uh, m dot infinity, which should come from a infinity. Okay, so uh, based on that m dot c2, you should find the pressure ratio, and that pressure ratio should be matching the that pressure ratio across the compressor uh, uh, should be uh, you know accomplished by the turbine. Okay, so the turbine should give that work to the compressor, and while it is doing so, the mass flow rate that it comes out of the turbine should also match with the mass flow rate through the nozzle. So uh, I hope you can understand all these connections together and view it as a, the principle, view the principle in a little careful manner. So all these components and all the pressure ratios are connected. There is no more it is like you will be given pressure ratio and you are expected to find what will be the pressure at the exit of the nozzle. It's no more like that. You will be given T04 and you are expected to find fuel air ratio. It is not like that. You have to know that the engine is given, and for compressor and turbine you know the operating maps, so you know the operating conditions, operating characteristics. For example, in the compressor it can operate in these ranges of pressure ratio, in these ranges of corrected mass flow rate. These are the efficiencies that you have, and the speeds at which it can run. So that is the compressor map that is given. Similarly, turbine map is that is given. Okay, now uh, in this whole operating different operating conditions, you need to find, if I want to run my engine at cruise condition at 7,000 meter at mark number of the flight speed of zero point 0.8. Okay, at flight mark of zero point 0.8, you should know which point in the turbine map and you should know which point in the compressor map you should select, which will lead to T04, which will give you a T04 by T02. And that should be your settings in your engine. Okay, so that should be your, and for example, from T04 by T02, you get F, and that F should be the fuel flow rate in your engine. And based on that fuel flow rate, your engine will adjust itself for that condition, and it will provide you that whatever the thrust you are expecting it. And also that is important because that the thrust that you get from that engine at that altitude is will determine what can be your flight load. Okay, so this is just engine component matching that you are doing here. In addition to engine component matching, you should also match this engine to the aircraft. Okay, so when you have an aircraft with certain load and the wing having drag lift coefficient, uh, what is the drag and lift, and its relation on weight and uh, thrust. Okay, so that equation will also additionally pose a constraint to your matching. Okay, and uh, so if you try to vary your flow rate, what happens is your mass flow rate changes, and because of mass flow rate, enough thrust will not be provided. And if the enough thrust is not provided, enough lift you will not get, and because of that you will lose altitude. And when you lose the altitude, your pressure at the inlet increases. That will provide more mass flow rate, and when the mass flow rate comes in again, the thrust again increases, and in the thrust increases again, it will lift the aircraft higher. Okay, the lift will increase and that will lift the aircraft higher. Okay, so this is a full feedback loop, and again everything comes into an equilibrium point. So that equilibrium point is what we are trying to find out through this bunch of expressions. Okay, so for this, it's a simplified a problem. It's a simple toy problem for you to understand how this whole thing operates. But ideally you should include all the other things that we discussed in the lectures. In the lectures, we have given a detailed discussion, including A infinity and other things. So you follow that kind of rigorous approach in order to come up with in order to do this matching and find out an off design, if you want to find out the operating conditions for the off design points. Okay, so uh, it is also it's also used when you have a, so let's say you are designing a flight and you have what do you call uh, uh, the so let's say you take a Boeing flight or Airbus A 320. So every um, flight will have its own mission profile, right? So it will be used for certain missions, and the mission will require different thrust at different you know operations or different during different stages in your mission. You may require different thrust and different performances, and those performance and thrust will be obtained only through this component matching procedure. Okay, because your engine is designed and it has been installed in the aircraft. Okay, so if it is a 2 or 4 engines will be installed in your aircraft. So once you install it, um, you should identify what are all the expressions that is going to be necessary in order to do this component matching analysis. So the expressions is so simple. You need to do mass and energy conservation for all the engine components, and the momentum conservation for engine plus aircraft. Okay, and you will end up having a bunch of equations, and you solve all these equations for different operating conditions, and you will end up drawing an engine operating lines as a separate graph, and that will be used in order to maneuver your flight. Okay, that is actually coded in your electronic control unit in your ECU of your aircraft engines. Okay, so this is the idea logic behind. So whatever we discuss is still preliminary. Whatever we discussed here is preliminary, and whatever we discussed in lectures is little bit even more involved and advanced. But that is also preliminary in terms of what they do in the industries. In industries for an aircraft, they are going to it is just not any simple equations like this. There's also turbofan engines there, and it will pose additional constraints in your engine components. So um, they include all this, and they have separate even more uh, rich procedures to do the same analysis. So the logic behind is same. Every component is going to interact with each other, and it is going to interact based on certain law, and that law is nothing but mass, momentum, and energy conservation. Okay, in fact, for engine components you have mass and energy conservation. So if you satisfy all this, then you can easily find out what is the operating pressure ratio and the turbine entry temperature and the fuel air ratio you should give in order to achieve certain design point. That is the whole point of doing this exercise. Okay. I am aware that this problem is not been asked in the week 12. Uh, there's no such problem in week 12 assignments, but it would be uh, interesting for you to have an hands-on experience in this kind of problems. Okay. All right. So, as I said before, if you have any questions, please feel free to use this common forum. You can ask your questions, um, and prepare well for your exams. Uh, and thank you. So, if you have any questions, you can stay back and ask. If not, thanks for attending. I also thank Professor Chetan Mistry for this opportunity to be a tutor for this course. All right. Thank you, everyone who's. Thank you, Krishna Kumar, and also thanks for everyone who's viewing from YouTube, who's going to view from YouTube. Uh, it's a really good experience. Thank you very much. All right.